of the day. Xiao-Chuan, please, if you can share your screen.
Can you hear me?
Yes, yes, we can hear
right.
you well.
Okay, before that, I also want to tell some interactions between me and Lorenzo. So Lorenzo, happy birthday to you. It's not long, so it's like 4 years ago when I think 4 years ago when I defended. It was the first time that I actually met Lorenzo. He went to my defense. He is not in my committee. He's out of interest. He went there. I mean, he's caring. But at the time, I was kind of too shy to start a conversation because before that, I never talked to him. Okay, big guy in the circle. And so I missed the chance. I didn't talk with him at all, but I noticed he was there and he was quiet. He listened to my defense and he left. And the real interaction between me and Lorenzo was actually at Iran. While several months later, after my defense, I visited Iran, and I talked with him. We spent some time, I think 1 week, 2 weeks maybe, together, and he's very nice to me. We discuss many things. I still under a lot of pressure. I don't know where to go after. I mean, mathematically. What to do next? Okay, I defended, I have a thesis. And Lorenzo told me something that was important until this day. He told me that don't stay in your comfort zone. Try to go abroad, try to visit as much as possible, try to talk to different people as much as possible. And I took his advice. After that, for a year or 2 years, I traveled like crazy. I meet all kinds of people. And actually, exactly during the time I was at Iran, Andres Kropecki was there too. And that was the first time I started to talk to him to learn something I never know before. I mean, before my thesis, I was focusing on differential dynamical system. And after that 2 weeks, it was intense for me. I talked with Andres, and he introduced me later to know Fabio Tal and the group at USP and Salvador Zanata. So I basically entered another field. I mean, Lorenzo kind of started it unknowingly. So today, okay, let me share. So okay, so it comes today. I will talk about what I learned after my defense. This is kind of important. And so I wrote in my abstract theorem, which is almost finished up.
Xiao-Chuan,
yeah.
Should I introduce you? Just for
yeah, you can. Okay.
Okay.
Yeah. Okay.
So it's a pleasure, a bit of force to introduce my friend Xiao-Chuan Liu from USP. Please, Xiao-Chuan.
Okay. Yes. So and in my abstract, I announced this result with Fabio, but due to the technical nature, I decided to only introduce the statement at the end of this talk, and I will not give the proof of this theorem. But instead, I want to go very slowly. So I didn't prepare slides. I will actually write down the things. I will go slowly to see how we are motivated, what kind of questions we are interested in. So, but for that, before I forget, the technique we will use, which I will not talk, is a very strong result called the forcing theory for transverse trajectories on surfaces, obtained by Fabio Tal and Patrice Lakovitz recently. And it's too technical, so I will not talk about it. We use this tool to solve some problems from here, which I do want to talk about. So this is a theory called a rotation theory on two torus, which is not a big area, but it provides very nice questions. So we are interested in a homeomorphism on T2, two torus, and we ask it to be isotopic or homotopic to the identity. So we put a 0 here. So for some reason, because the notion I'm going to introduce makes sense. So this means homotopic to identity. So F tilde is the lift, some lift of F. You always use this notation. So we have this picture. So what we have is that here we have a torus, and we have a dynamic, which is only, this is actually an area of topological dynamics. So I only have homeomorphisms. So here I map X to F of X, and I have a lift, which is F tilde, and here I map X tilde to Fx tilde, something like this. We are interested in the displacement, so we introduce this. Consider the displacement function. So I denote dirt of F tilde. So it is defined with respect to okay. So with respect a chosen lift, but it is a function on X downstairs. So it is defined as this vector. I mean, you can check that this is a function on X. It does depend on the choice of F tilde, but it does not depend on the choice X tilde. So it is a function on X, on the torus. So we measure this is just on the lift. It measures the one-step displacement of this function based on X. If you see it in the lift, in the universal cover. And with this, we can define our main character, which is the rotation set. So we define the rotation set of F tilde to be this kind of average displacement of X, d mu of X. When you consider all mu, mu is F invariant, Blair probability measure, on T2. So you consider all the invariant measures on T2, and with respect to different invariant measures, you can make this expression. It is actually gives you the average displacement on the lift, and you allow yourself to change the different measures and to see this value, and you gather all the possible average displacements. So you call it a rotation set. The point is, this is not only a point. If you do this for circle, for example, one-dimensional object, we are more familiar. So it's like the first several weeks when you're learning dynamical system, you want to learn the dynamical system on the circle. You give you a homeomorphism and you leave it, it's the same thing. But there you obtain a unique rotation number. And here it is should be a number in R2, but it's not unique. It's not a one vector in R2. It's not one point in R2 in general. So when people started to learn this, actually this definition was given by Michel-Herman. And later, this definition is not, I mean, there are a better definition in some sense given by Mizrachi and Zeman. And they are equivalent. I will not write that. It's not difficult, but the definition given by Mizrachi and Zeman is kind of gather all the subsequences and to look at this is like the space average. That is you take all the subsequence of nk and you measure the time average, and it turns out it's the same thing. But it takes some effort to prove they are the same thing. For example, let's talk about some properties this set satisfy. For example, this rho F tilde is always a compact, and the convex subset of R2. So this property actually follows pretty easily from this definition. But if you make another definition, which is that Mizurovich and Zeeman definition, where you consider all the subsequence and you consider the time average, you have to take some effort to prove it is convex. But anyway, you can prove these two definitions are the same. So the second property which I want, so this gives you three options. Either it is a point, which is just like we are in one-dimensional case, which it could be a segment, or it is something contained interior, compact. Is there a question? So, okay.
Yeah, sorry,
Oh,
is this function, sorry, I may have missed the point. Is this function additive, sub-additive, almost additive?
This function?
Uh-huh.
Yeah, it should be sub-additive, I think. Yeah, let me see. Yeah, it's bounded. It's every yeah.
Okay. Well.
Yeah, right. So it's like you are starting from x tilde, and the next time you arrive at x2, and next time you have a triangle inequality, and it gives you sub-additive. I mean,
anything stronger, like almost additive?
Like what?
Almost additive.
No, I don't know. I'm not sure.
Okay,
I'm not
okay.
sure the notion. So okay. Yeah. So okay. So there are several cases, and the second property is that these things were proved in early papers when the notion was explored. So every extreme point of rho of f tilde can be realized by an ergodic measure. Meaning that if you choose, so for example, you take your rotation set is like this, and you choose a extreme point. This is extreme point. Extreme point means that it cannot be written as, so this guy is not an extreme point. It can be a linear combination of two other points. See, but Q is an extreme point because it cannot. So any extreme point Q here of your rotation set can be realized by some ergodic measure mu, meaning that if you put in this mu here, it gives you that rotation vector. So Q here I write belongs to R2. So it's a vector. Okay, so every extreme point can be realized by an ergodic measure. And maybe I should talk another, because if you are first time at this, you might ask the dynamical implications of these notions. So it's kind of important to know that if rho of f has interior, the third case here, then it implies that you are chaotic. So your topological entropy of this guy, okay, of f, is positive. So this is kind of important. It was first proved in a paper using Thurston's surface theory, and very recently Fabio and there is another proof using forcing. There is another proof, and you can actually try to estimate this entropy and okay, that's other thing. It's not a topic of today. So I think to me the most important two topics in the area is one, the shape.
Excuse me, Xiao-Chuan.
Yeah.
Can I ask a question? In the condition 2 that you wrote, that measure that appears, do you have any information about it? Let's say like its entropy or something like that. Even let us assume that the rotation set is what you draw, it's like a polygon.
No, there. Okay, so if this is a rational point, then you have a periodic orbit, then you have a periodic measure. If it is an irrational point, something totally irrational, I mean, each coordinate is irrational and their quotient is irrational, then you have something that the support of the measure is a contour set, which is pretty complicated.
Okay.
In fact, every point inside in the interior here, every point in the interior here has a corresponding ergodic measure too. So it makes the picture even more complicated. So every rational here, you have every rational guy here, you have a periodic orbit. Every irrational here, you have a different counter side. So you have you can imagine a lot of different. This is a very complicated. So in the dynamics of the torus, you find a lot of different counter sides. They move with totally different speed. Okay.
Sorry,
Okay.
can you repeat again? Every value is realized by an ergodic measure?
Yeah, every, so probably I can write here 2 prime. So every p, every value p in the interior
Okay.
of the rotation set is realized by an ergodic measure. And moreover, if this is rational, it is a periodic orbit.
So what about this? So
If it's irrational, you have something which is yeah, it's an ergodic measure. Support is interesting. It's some counter side, and there are a lot of counter sides there. So
Rational means the two coordinates, rational numbers.
yeah, 2 coordinates are called 2 coordinates are all irrational, and their quotient is also irrational.
Okay, thank you.
So otherwise, maybe you lying in some strip, but that's so. The first is possibly the possible shape of a rotation set, any rotation set. So people trying to achieve different shapes. For example, if you can find something like a disk. So this is very difficult. I don't know anyone is working on this. I heard that Artur and Fabio, they are trying to do something like the boundary is like a counter side, something weird. The boundary is not, I don't know. So they are toward this conjecture and discuss for some time. So I don't know any real progress in this direction. So I mean, actually, it's very hard to find something that you actually find something with curvature on the boundary, which gives you a rotation set. But anyway, this is not our topic today. So today I want to do the second one. How does the rotation set change? Depending on the dynamics. So I will be a little interested in when the rotation set. So consider dynamics is changing along some one parameter family, for example, if you want, or any you fix f and you just perturb it a little bit. So I want to know how the rotation set will change with that. So obviously these two things are connected, but today I'll talk about this. So let's talk what I mean about this. Let's talk about a simple example, and actually I give proof, which is very simple. So consider the minimal rotation. So where alpha beta is I mean the translation. So where alpha beta is totally irrational. This is a minimal on the torus. So meaning that alpha irrational, beta irrational, and alpha divided by beta is also irrational. So totally irrational. And this is a minimal on the torus. And I want to say that R, this R, let's just denote R here, the rotation. So R can be C0, only in the C0 category, approximated by some G such that the rotation set of G has interior. So I make any absolute perturbation of R. I obtain some dynamic G such that it has interior, and alpha beta, which is the rotation set of the original map, is contained in the interior of this rotation set. So this is actually an exercise, but I want to give a proof of this. So how to do this? So consider we have here any point x0. Let's write this is my torus, and I have x0. I draw this line is in the direction. So this line L is in the alpha beta direction. And this is the perpendicular line. Locally, I found a little region I call omega0, omega1, for example. So this shaded region is called omega1. It's a small region, not far from x0, but on this particular region. So for x0 in the torus, there exists some n very large, such that Rn of x0 will lie in this omega1, because my dynamic is minimal, right? And also I ask this Rn of x0, it's very close, it's epsilon close to be x0, like in the picture. And then use, I told you this is very simple, use C0 closing lemma to find a perturbation G, I said G, right? G, such that it close it. Remember, the R, when R maps some point here to Rn of x0, it has rigidly, it has rotation number alpha beta. But after the perturbation, you push it a little bit. So here, this after the perturbation, you push a little bit to get a periodic orbit. So this periodic orbit sees a rotation, a rational rotation number, like lying, but this rational rotation number is lying. So suppose this guy is alpha beta, and I call this region omega 0. Before I call omega 1, here is omega 0. So this new rational number must lie in omega 0. It is because you are a little faster, you move a little, you perturb a little, you are a little faster along that direction, and you average by n, you see a rotation number here. So do this for 4 orbits, for 4 pseudo orbits, if you like, epsilon pseudo orbits, and close them together, all together. So at the same time, so you obtain some G such that rho G will contain 4 points, for example, and 4 points, for example, and alpha beta is in the interior of it. Okay, I think it's a full proof. So it's a simple proof. But it's still interesting. For example, for C1 case, you don't know if you can do this successfully. It's a little subtle. So it's still, I didn't go that, but for C1 it's not sure. But for sure for CR, sometimes this does not work. So the first remark I want to make is, I think, okay, here is the only remark. So I want to say is that in higher dimension, in higher regularity, in D field of R of torus, if you choose, one can, so R is sufficiently large, one can choose alpha beta to be Diophantine, whatever it means, is a very special subset of irrational numbers. And due to Diophantine, due to KM phenomenon, you can prove that you cannot do this. So actually, there was a precise result done by Calallius. He was here at Rio at some point. He proved that if you choose this properly, you can either, after your perturbation, your rho G is alpha beta. You can actually conjugate it back. You can conjugate it back because of the KM, or rotation set of this misses alpha beta. So what I did just now cannot be done for higher regularity. Okay. So I mean, I only want to say that this does not come for free. And Okay, there will no proofs. I think I have 5 minutes. I'm 5 minutes late, so I'll have 10 minutes, I hope. So I'll
Yes,
compare.
yes, you don't have 10.
Okay, I hope I have 10 minutes. So I only want to, I want to compare some results and jump into current research and to say this perturbation, what kind of things you can do about it and what you can. So I'll start with okay, I'll skip this result, I think. So Zanata, Salvador Zanata proves that whenever on each extreme point has alpha beta on your, I will not write this, so I don't have time. So alpha beta on is an extreme point, and it is not, if alpha beta is not in Q2, then in C0 category, you can always so sorry, alpha beta is not in Q2 and lies in the boundary of your rotation set, then can perturb it to G such that rotation set of G at least contains something. So this is not empty. So this is a clever application of Atkinson's lemma in ergodic theory. So I think I will skip this because I want to talk about more. So this confirms of our elementary actions.
Sorry, in the condition is if alpha beta belongs or not belongs.
Sorry, it's wrong. So is an extreme point.
But before, alpha beta is not an irrational.
Alpha beta is not rational. At least one of the coordinates is irrational.
Okay.
We did in this exercise, in this example, we did it for totally irrational vectors. But we ask more. We find something which actually blow up and contained. Here, the condition is that only one of them is irrational. It does not belong to rational. But alpha beta is the extreme point. So then the conclusion is that we can see something outside the original rotation set. So rho of G minus rho of F is not empty. That's a little weaker too, the conclusion. So this is but the general philosophy is that when you see an irrational vector, a little here is one of them irrational. You can't do it. You can't perturb it. But however, there is another theorem I want to say is due to Zanata and Lacroix. This is fairly recent. That okay, so you have one parameter family. So actually, you can consider either area preserving analytic map, or you have one parameter family generic. Of CR diffuse. R is pretty large. And suppose those conditions. First thing is that there is a rho 0, which now it does belong to, so fix this. So suppose fix a rational vector. Suppose that this guy does not belong to your rotation set when t is smaller than t0. And it does, so when t, some t0, when t equals t0, it does belong to the rotation set of f tilde t0. Actually, this is the first time, t0 is the first time that rho 0 belongs to your rotation set. So it means that it's on the boundary. You cannot jump into it. So the conclusion is that then for t greater than t0, so when you pass the critical point, the parameter t0, but not far, so still close, meaning that you are larger than t0, but t minus t0 is smaller than something. So then rho 0 cannot be contained in the interior of the rotation set of t. Okay, so how to understand this? I give an example which, okay, so there exists, I will skip the details. So there
It
exists.
either leaves the rotation set or remains in the boundary for some time.
Yeah, you can, the thing
Or
is that
intertwined.
this is the rho zero. You have something that this is the rotation set of rho t and rho of ft. You grow, and at some point at t0, it becomes in the boundary, but you cannot eat it. So which is a nice example is the following. There was a early example which you have f such that the rotation number is this. So this is 1, 1, and this is minus 1, 1. So the rotation number is minus 1, 1 square. So this is a very clean example. I don't want to write a definition. Definition use sign functions. Okay, so there exists a function. The rotation set is exactly this square. So one of the consequences of this theorem saying that there exists some epsilon such that any epsilon perturbation of f, let's call it g. So g is epsilon perturbation. Rotation set of g must be contained in this square. Exactly what I mean. So here, because all 4 exponent extremal points, so this is are all rational, and you can make a parameter and such that for time t0, this is exactly your rotation set, and no matter how you perturb it, it is contained here. So these 4 guys are like guards. You cannot really escape. There is a little epsilon in C0 perturbation. Any perturbation you have rotation set is contained here. This is called mode locking, rational mode locking. Okay, so this is something motivated us. So okay, so
but
after
Xiao-Chuan,
this,
you meant some generic family. What does that?
Okay, that's a nice question. I lied because there are parallel theorems. They also prove that if you're analytic, you don't need a generic family. So here, this function is analytic. That one function is okay. So it satisfies this theorem. So it is also true if f is analytic and area preserving, and the conclusion are true. So here, f can be written down. So you have to use some sign function, and it is analytic. Okay, thanks for the question. Okay, so after that, okay, Salvador and I did something. We look at the rotation set of this set. So what about if one of these guys is rational and the other guys is irrational? So this is simplest example we can think of. So if rotation set is like this, and we're trying to understand the perturbation results of this. So in the end, we can perturb such that the rotation set will be like this. Something eaten the irrational end, but here is like a guard here, you cannot do anything. So during the time we sensed that. So there is a part 2. I don't know if I can, okay, give me 5 minutes. We sense that a notion is kind of important, bounded displacement.
Xiao-Chuan, a quick question. The last
Yeah.
result that you mentioned of you and Salvador, what is the regularity of the perturbation?
C0.
Zero?
Yeah, C0.
Okay.
Okay, we need a condition of non-wandering also. So it's we need f is non-wandering. But okay, it's a little weaker than area preserving, but we want to do this, we have to assume it's non-wandering, and then the conclusion is only C0 perturbation. The reason is the same. Even in that example I just gave, it's hard to give some regularity. We have to do something more complicated to make the perturbation, and too many orbits, all pseudo orbits, but too many of them. I don't know how to do C1 perturbation. I don't know. I have no clue. So, and okay, so bounded displacement. What does that mean? So, choose a vector, a direction. So V in R2. So we define, say, a lift F tilde has bounded displacement. if along this direction there exists M such that the projection along this direction, you consider the inner product. You have a of F tilde N of X tilde minus X tilde. This guy is always controlled by M. So it is bounded in that direction. So I really read this very simple, very concise, and I will state the result. So here is a direction V. And suppose you start from X0 here, and you iterate your dynamics, you obtain F tilde N of X tilde. So here, suppose here you have a line with distance M V along this direction V. This conclusion simply says that for all positive iterates, F tilde N of X tilde 0, they all belong to the left part of this line. So along this direction, the displacement cannot be M away. Okay. So finally, I can state two results. The first one does not belong to me. It is a thesis of Guilherme Solomon, as a student of Fabio Tal. They show that this is already published. When you look at this rotation set, then suppose F has this rotation set, and suppose V is a perpendicular direction of alpha beta. It just means that if either you take V to be minus beta alpha, or V is beta minus alpha, you have only two directions. V is one of those. Then F tilde has bounded displacement along V direction. So the second result is recently almost finished with me and Fabio. Sorry for my handwriting. So the same rotation set conditions as the previous theorem, and we assume F downstairs on the torus is non-wandering. Then along minus alpha beta, F tilde has bounded deviation displacement. Yeah, we discussed further. So after this work, we discussed further. This can be removed. I believe that this, but there will be a second work we are trying to draft in the future. But at the moment, the whole picture of this rotation set gives you is that okay, if so with these two theorems, we see that if your rotation set of this guy is like this, 0, 0 and alpha beta, on the lift, you start from any point x0. It's kind of this is the direction of alpha beta, and this is the perpendicular direction. You put M here, you put M here, and the backward you put M here, and these three directions, this direction, this direction, and this direction, they are all bounded. It means from any x0 tilde, the forward dynamics will never leave this region. So this could be useful in the future to construct some foliation-like structure to understand the dynamics which we are discussing. So okay, so this is a plan for my talk. Hope you enjoyed.
Thank you, Xiao-Chuan. Let us thank you. Before I open for questions, I have two announcements short. One is that there is the attendance form to be filled for who wants to get the certificate. Is on the chat now. And the second one is that when we finish this talk, is the last talk of the day, but will be some breakout rooms to continue the discussion. So we don't need to leave. If you want to stay, you can stay after the questions. So
May I also?
now,
Okay, sorry.
yes. So we can say
I want just to make a propaganda from the Mesa Redonda tomorrow. May I?
yes, yes.
Okay. I just.
Let's
Okay.
first
Zezé, vamos
continue with the
terminar.
questions.
Continue with the
please.
Yeah,
questions.
let's hear the
Okay,
questions
so,
first.
a Jaqueline que começou com anúncios antes.
Nem a Shea Lady tem direito, Zezé.
Ah, tá bom. Ok.
Okay, so okay, so is there anyone has a question or a comment?
Xiao-Chuan, could you put your slides again?
Yeah, right. Yeah.
So could you quickly explain that example that you did at C0 perturbation above? You use the C0 closing lemma somewhere.
Okay, yes, you have to find enough pseudo orbits and you connect them, and so you have to use.
Could you go up where you wrote?
Yeah. This guy. This guy, right?
No, above.
The example.
Yeah, the example.
Okay. Yeah, I mean.
Yeah, here, exactly.
Yeah, right. You just, I mean, you start from x0 and so locally, if you scale this, you have x0, and then this guy is Rn of x0. And if you one step before, you are Rn minus 1 of x0, right? It jumps here. And you draw a little curve like this. And you put a very little domain open disk like this. And you define something phi, which is supported here. And it maps your Rn of x0 to x0, and you make the connection. So it's pretty arbitrary, because if you are C1, you have to consider the scale of this thing. But you are only C0. No matter how many orbits you want to do this, you can make this small enough, they don't influence each other. So that's the reason you can do several pseudo orbits at the same time and achieve this. And
why can't you do it in? How do you use KM theory to prevent it?
No, that is I don't know. I mean, it's a little complicated, because you use, so if alpha beta is in Diophantine, I mean, this is a condition, and then you can put it very strong Diophantine, and then basically I think what is that if your rotation set, if alpha beta is contained, so the statement is if alpha beta is in the rotation set of G after your perturbation, then you can conjugate. So after some conjugation, so G is conjugated to the rigid rotation. Do I lose signal? I don't know. Can you hear me?
Yeah.
Yes.
Yeah. Okay. So I mean, you use Km to try to conjugate any perturbed. Either it means alpha beta. If you see some speed alpha beta, you can conjugate it back. So after you can conjugate it back to alpha beta. If you have a conjugation, then it means that your rotation set is alpha beta, 1 point. In particular, you cannot get something with interior.
But can't you use, instead of this C0 perturbation, this C infinity closing lemmas that people are proving recently?
I don't know the full scale of that C infinity. I think you must assume some other area preserving and some other. I didn't check. I don't know. I realize there is some version of C infinity closing lemma, but I don't know if it fixed here.
I guess that in this closing lemma, you don't have control of the orbits. I guess that you get an orbit. Hello?
Oi.
I guess that in these closing lemmas, you don't have the control of the orbit. You simply know that you have an orbit. And probably Here is completely crucial to have a control of the orbit. Probably you need something like an ergodic closing lemma. I don't know. It is really tough. But I guess that I don't know. Somebody gave a talk recently and mentioned that this kind of connected lemmas. Well, you have the connected lemma, but that's all. You have no idea about the.
But this result was published. I mean, regarding this result, it's interesting maybe to make some comparison what cannot be done at all. I mean, this result is for some CR you cannot do it. I mean, this result by Liu. He is a student of Krikorian.
Still in the example, Xiao-Chuan,
yeah,
I got a bit lost, but is it known, this example, just this simple example, for C1 perturbation, or it's not known?
I don't know, but I think I don't know. So to answer your question, I don't know if this is known for C1 perturbation. But to answer your question, there is a theorem I skipped, is Zanata, which when you see one irrational number, then you can perturb kind of weaker in some sense, both conditions and the results. You asked me this when I talk about this. So if you have this is not rational, this result, and then you can perturb it to see some, this has a C1 version. By your co-author from France, it has a complete name to me. It's Pierre Doigt.
Pierre-Antoine.
He was a postdoc with Andres.
Ah, okay.
He has a result. He did the Salvador's paper in C1.
Ah, okay.
Yeah, this result exactly. But this I don't know. I didn't see anyone read this. Actually, this example I wrote it with Salvador in our papers. So
because I got the impression that Lorenzo's suggestion would work. Because maybe in C1 you can use the ergodic closing lemma. Because with the ergodic closing lemma, you have more control of the orbit.
Yeah, maybe, but maybe it can be done. It's I don't know if it's difficult or maybe it's just an exercise. I'm not very familiar with C1 techniques, so.
Okay. Thank you.
More questions or comments?
Maybe I have a comment because this is a school, and so maybe this. We can relate the talk with Poincaré rotation number for the student that most of the students here know, and there are other generalization about it. The Neuhaus-Palstax, I think so, that introduced the idea of generalize the concept of Poincaré rotation number for endomorphism of the cycle. And in that case, you already have a interval, a rotation interval in many cases. And Catherine asked about if the difference between if that difference was subadditive or something like that. The answer in general is no, because for instance, if you have a positive entropy, you're going, and in this case, you're working a surface, so this means a Hochschild, and in this case, you can take, there are many orbits there that you have a historical behavior, for instance, and you can use this to produce orbits that the average of that difference not going to converge, and so this means that they must not be subadditive. So and so only to connect things, because I think it's for the students maybe, because this is a very interesting talk, and this is a generalization of Poincaré rotation number. So.
Yeah, thanks, because I didn't answer it correctly. I didn't think that way. I was kind of yeah.
No, but Wilton, I mean, there would, even if it would be additive, then of course there's almost always historic behavior, but it would be almost always exist. limit. I mean, it's always-
This depends of the dynamics. No, if, for instance, I don't know precisely of the dynamics that is a C0 dynamics, diffeomorphisms.
Which one?
You are working in this the results. You can put again the
final result.
Not really.
The final result. The final result is only C0. And
I mean, Xiao-Chuan is working the moment.
Fabio.
It's just homos. The dynamics is just homos, but I don't think the function is subadditive in any sense. I mean, it's you don't need to have convergence of this, and you might get that for almost all Lebesgue. You might preserve Lebesgue and have, well, not if you preserve. You might have that for almost all points, Lebesgue almost all points, you don't have a convergence of the rotation number or something like that. So it might happen that almost all points doesn't have a convergence, but if you don't preserve Lebesgue. If you preserve Lebesgue, then by Birkhoff-Ergodic theory, I mean, almost every point is going to have a rotation number. So, but I mean, it's not. The function is not going to be subject. It's a little difficult to define so that it's a function on R2, right? I mean, the values it takes it's on R2, not on R. But I'm just saying that you don't expect to have convergence everywhere in general. Right? I mean, you don't have well-defined rotation numbers mostly.
Yes.
All right. More comments, questions?
Have I the right of making one more question?
Okay, if it's short, yes.
Yeah, it's just, I guess. So, Xiao-Chuan, I know that you want to drop this no-wandering condition, but if you impose something stronger, like error preserving, can you draw stronger conclusions?
I mean, we are more like trying to remove all conditions. I mean, we work with non-wandering setting in our mind. It's basically area preserving, but we are trying to go to another direction, trying to remove this. Really, to see this is kind of what we are aiming at in topological dynamics. We don't really.
But if you assume error preserving, it doesn't help you more than to nothing.
I mean, I think it's more. Actually, things might be easier if you put error preserving in some sense. You have enough recurrence, and without that, more weirder things happen in topological world, and we like that weird things. It's continue, and I mean, yeah, I don't know.
Thank you.
Okay, so let us thank Xiao-Chuan Liu again, please.